In the previous lecture, we talked about how to analyze mechanical properties, but mechanical properties are not the only property that are important to understand when you're looking at polymers or plastics. So I'm going to talk a little bit about the chemical and physical properties analysis that is often performed. So thermoplastics get their strength from molecular weight, and so understanding how molecular weight varies or molecular weight distribution varies in a thermoplastic is important. This can be determined by many different methods, as it is very important in polymers. But the one that we tend to use the most is GPC, or gel permeation chromatography, or size exclusion chromatography. We can also do things by viscometry or by light scattering, but chromatography is kind of the workhorse of determining molecular weight. So this is kind of a schematic of gel permeation chromatography. A series of boxes. What is really actually happening is you dissolve your sample in a solvent, which is also known as the mobile phase. You inject it, you have a solvent within the system as well. You inject your sample into the column. The column doesn't look like a big column. It actually is very narrow. It probably is around the size of less than a drinking straw. So, but that column has a lot of material inside it, and that's what this is present here. So when you load your sample into the column, your sample goes in here. The solvent that you've dissolved your sample in and the solvent in the system flows through it. Small molecules get hung up in the gel, so we see our little small molecules here, whereas large molecules can't get into those little spaces in the gel, so they just kind of wash right through. And then these are detected at the end by a specific detector. Sometimes it's index of refraction, sometimes it's a spectrometer at the end that detects the molecules, but that gives you an output that shows you how the molecules are separated as they go through the column. So gel permeation chromatography is used to determine a relative molecular weight. There is relative molecular weight, and then there is absolute molecular weight. What this does is relative molecular weight. GPC truly measures the volume of a molecule in a solvent, which is called hydrodynamic volume. And if you have a reasonable solvent for your molecule, that relates well to the molecular weight, but is a relative measurement. Also, you get a distribution of molecular weights. And what you see is this output here. You have time versus intensity. Smaller molecules enter the pores more easily, and so they come out at higher retention times. They're retained within the column longer, whereas larger molecules don't spend a lot of time in those pores, if at all, so they come out sooner. So these are the large molecules that are present in the system, and these are the small molecules that are present in the system. The large molecules do not permeate the gel as well, and the small molecules do permeate the gel. So that is why it's called gel permeation chromatography. This also is called size exclusion chromatography, because the large molecules are excluded from the column, whereas the small molecules are retained. We also do a lot of chemical characterization of the backbone of the polymer. Now, whether you like to believe me or not, the chemical backbone of a polymer has a lot to do with its actual properties. And the one that I like to use a lot is infrared spectroscopy. We will do this type of spectroscopy in lab. There are a wide variety of other spectroscopy, but infrared is the one that's often used in QC labs, or it's very easy to maintain. The overhead for this particular type of instrument is low compared to the other types, so infrared is typically what you see in industry if they have a spectrometer. So what do you get from infrared spectroscopy? Here you have your schematic of the instrument. This is your output. So what you get are a baseline with a whole lot of squiggles on it. Doesn't this look like a huge mess? It is, but if you know what each one of these bands corresponds to, you can actually see the chemical groups that are present in the backbone. So I did this for 5 years, looking at one specific molecule for 5 years, every single day. So if you want to show me a nylon, I can do it by just the way this particular spectrum looks. So this one is a silicone, or polydimethylsiloxane, and it has very characteristic groups for a polydimethylsiloxane. And so where these show up specifically correspond to a particular atom or group of atoms in a backbone, so you can make determinations about the type of polymer that you have. In the infrared, when we refer to infrared spectroscopy as part of the electromagnetic spectrum, but infrared light is actually what we consider to be heat. And the area of the infrared that we look at is the mid-infrared, which is 4,000 to 400 inverse centimeters. And this isn't a typo, this is the way it is represented on the spectrum. Molecules will absorb energy from that heat laser that's being bounced off of it, and they have resonant frequencies. So the transition energy of the bond or the group that vibrates corresponds to a specific band. You have to have a dipole or asymmetry in a molecule. So this is nitrogen, this is a symmetrical molecule. You won't see that in the infrared, but you will see carbon dioxide. So for example, carbon dioxide usually hangs out right about here. So if you have a lot of carbon dioxide gas, like in the air, you will see it. So different groups of atoms or functional groups give rise to specific characteristic bands in both intensity and position on the spectrum. And from there, you can say, oh, I have a silicone, or I have a nylon, or I have a polyolefin. We also do a wide variety of surface characterization methods. One that is often done is scanning electron microscopy. And microscopy is largely just as a series of pretty pictures. But those pretty pictures can tell you an awful lot about surface roughness or surface morphology. And morphology is just a fancy way to say shape. So this is an example of electron microscopy. Now, some of these may look pretty obvious, like say our friend down here. That is a spider that's been put in the electron microscope. This is some sort of knit material that's been put in the electron microscope. This is what is known as a non-woven breathable fabric, like say on baby diapers or something like that. And this is pollen. So if you have seasonal allergies, this is your enemy. But electron microscopy can give you lots of information on a very small scale. But why do they look like this? Why are they all black and white? Why do they look like this? It's because you're not using a light beam. You're using an electron beam. And what you have to do in order to get these samples is to coat the surface. And so you have a focused beam of electrons on your sample, but the sample has to be electrically conductive. And the way you accomplish that, so here's our friend the spider, is to put an ultra-thin coating of a conductive material, and usually that material is gold, or gold mixed with palladium. And you can get magnification ranges from about 10 to 500,000 times. For light microscopy, you can usually only go up to a couple thousand. So this gives much greater magnification for samples. We also need to understand how the material behaves in different thermal environments, and we use a couple different ones in the laboratory routinely. We use Thermogravimetric Analysis and Differential scanning calorimetry. I mentioned dynamic mechanical analysis here, but I won't go into it in too much depth. Thermogravimetric analysis primarily looks at degradation behavior. It's really important to know at what temperature your material degrades when you're choosing a material. You need to have something that withstands the type of temperature that part might endure. So if your part is going to be enduring, say, regularly 350 degrees Celsius, you want to make sure that material can withstand that and doesn't break down. And that's a way to do that. So here we have two different polymers. Here we have PEEK, or polyether ether ketone, and here we have PTFE, or polytetrafluoroethylene, or Teflon. So when we look at these two, you see one of them reaches very high temperature before it starts to degrade. So where this is 100% weight, this is 100% weight. The way you do this is you start heating this up, and once you start this to drop from 100 down below, that's where you start to get degradation. In other words, you're just burning the crap out of this in a nitrogen environment. And when you start to see this depart from 100% weight, that's where you're starting to get weight loss due to degradation. So in the case of this particular material, you have a PTFE piston ring. That one starts to degrade at about 500 Celsius. And then your PEEK ring starts to degrade at about 567 Celsius. These are very high temperature polymers, both of them. Now remember, this is Celsius. This is not Fahrenheit. This is not where you're broiling meat. This is much, much higher than that. Your oven does not reach this temperature. So these both went up to what appears to be about 800 Celsius in terms of the analysis temperature in order to see degradation of both samples. So how do you determine your upper use temperature for something? You take this and you subtract, depends on how you're feeling, but anywhere from 10 to 15 degrees to determine your upper use temperature. This is another TGA curve, so you see your weight loss. It can go in multiple stages, so you see your weight loss here, your weight loss here, and your weight loss here in the red curve. In the blue curve, this is actually differential. This is the rate of weight loss. So you have the biggest weight loss here, you have another weight loss here, and then you have another weight loss here. So what this probably is this weight loss here is probably moisture, and then you have a two-step degradation for this material. So this actually starts to lose weight after you drive off all the moisture at about 310. So this is a much less thermally stable material than, say, PTFE or PEEK. So you see a change in the physical properties and the chemical properties. So as a function of increasing temperature, you see mass loss. And that is indicative of the degradation temperature. You can do things like get decomposition patterns, and that's typically what it's for. Also, you can see the amount of inorganic content in a material, and that is percent residue in the output, but that is also what percent of inorganic filler you have present in the sample. And that's primarily what I use it for on a regular basis, is onset of degradation temperature and percent residue to determine inorganic filler. Differential scanning calorimetry is a lot more gentle in terms of the temperatures that you expose your material to, but it also looks at thermal behavior of a sample. So this is kind of a really basic DSC curve, but this is, say, your glass transition temperature. This is, say, a crystallization event, and this is, say, like a cross-linking or a melting event. One thing to pay attention to is what this says. If it says endo up, it means that anything that is endothermic is pointing up on the graph. If it says exo up, it means anything that's exothermic is pointing up on the graph. So these would be flip-flopped in an exo up type curve. But in this case, you have a sample, and you have a reference pan, and you have heaters. And the difference that you see is how much heat flow goes into this sample to keep it the same as the reference pan, which is empty. And that can give you information on whether it is going through a glass transition, whether it's crystallizing, whether it's cross-linking or melting, and then you can get information along those lines. Remember, the glass transition is an important parameter, and so is the melt temperature, and so is the peak crystallization temperature as well. So what we look for, this is calorimetry, and the definition of a calorie, or a kilocalorie that you see back on the nutrition facts on your food, is the amount of energy that it takes to raise 1 kilogram of water 1 degree Celsius. So that is the definition of a calorie. That is heat flow. And what DSC measures is the difference in the amount of heat required to increase the temperature of a sample versus a reference. So the sample holder increases linearly as a function of time, while the sample undergoes a physical transformation. More or less heat will have to go into that reference to maintain the same temperature, and that's where you see those transitions. So we look at those for fusion and crystallization events, in other words, cross-linking or crystallization, glass transition, oxidation, or other chemical reactions. And so typically your temperature range on this one, whereas TGA was like from room temperature up to 800 Celsius, this usually goes from -80 Celsius up to about 200 Celsius. So you can see different thermal behavior in DSC versus TGA. I'm not going to talk about dynamic mechanical analysis too much, but you can also get glass transitions from the dynamic mechanical analysis as well as some tensile properties like loss modulus or storage modulus. Other things we look at are thermal property tests like heat deflection temperature. This is usually where you see the softening of a material. It is the temperature at which a plastic sample deforms under a specific load. And the test procedure is outlined in an ASTM. So you have a 3-point bending specimen, and then you have a load that's present pushing down on it. The outer fiber stress for testing is either 0.455 megapascals or 1.8 megapascals. And then the temperature is increased at 2 degrees Celsius per minute until the specimen deflects 1/4 of a millimeter. So once again, everything here is in metric units, and that is typically how things are done for standard testing. That's just kind of how I think is in metric units when I'm talking about things in the laboratory, so keep those in mind. Other analytical methods. Electrical property tests like dielectric constant, electrical resistance, dissipation factor, electrical conductivity, as well as optical properties, index of refraction, optical clarity, absorbance and reflectance, as well as gloss. If, say, you have a coating and you want to see how glossy that is or how matte it is. Weatherability is another thing that's important for both plastics and coatings under certain light conditions, water conditions, and temperature conditions. We also look at chemical resistance, adhesion, and permeability or diffusion. Now, weatherability is done by accelerated weathering or QUV. And what you do is reproduce the damage caused by environmental exposure. So sunlight, rain and dew, and in the sunlight you're looking at UV radiation. And what you can do using a QUV is you can reproduce the damage that occurs over months or years outdoors. And these are things that you generally have to do when you're certifying, especially an exterior product like vinyl siding or, say, exterior paint. And the materials in the QUV are exposed to alternating cycles of UV light and moisture at controlled and elevated temperatures. The sunlight is produced by fluorescent UV lamps, and then dew and rain is produced by water spray. You can also reproduce, say, marine environment by using salt water in your water spray. Rheology is another important thing it's often for thermosets, but it is something that comes into play in thermoplastics when you have materials in the melt. Rheology is the study of deformation and flow of materials. I teach an entire graduate course on this, and there's a wide variety of ways you can measure rheology. The one that is of most concern when you're looking at thermoplastics is melt flow index. And you'll see this reported as part of the parameters of any material. So if you have a lower melt index, you have a higher molecular weight, higher melt viscosity, better impact resistance, but it's more difficult to process. A high melt index is a decrease in tensile strength, softening temperature, and toughness. What melt flow index actually is reported as is the amount of material that can go through a particular orifice in a particular period of time. So if you have a high melt flow index, it has low molecular weight, it melts really easily and a lot of it goes through. A low melt index means less of it goes through, has a higher molecular weight, so less actual material goes through, it has higher melt viscosity. Viscosity measurement is often important for materials. Melt viscosity when you're doing something in thermoplastic processing is important. I most often use viscosity measurement when looking at thermoset materials. We also have physical tests. I talked a lot about these in the mechanical test, but we also do things like hardness, abrasion resistance, and mold shrinkage, which also fall under the category of physical tests. So this concludes the chemical and physical properties testing. From here we're going to move on to permeability. Thank you very much.